Okay, so starting of Unit 4, functions and relations is what we're going to deal with today. Our learning objectives for the day is that we are going to determine whether a relation is a function. We first need to figure out what a relation is, right? In order for us to determine if they're functions or not. We're going to determine if these relations are functions by given ordered pairs, a graph, and whatnot. We're also going to find the domain and range and use the function notation. We will need to figure out what domain and range is and what function notation is. We're then going to use the vertical line test to determine if a graph is a function or not. And then we are also going to evaluate functions. Okay? A lot going on today. I fit it all on one page, front and back, though. So we'll get through these pretty quick. A relation. Some definitions. A relation is a set of ordered pairs. Any type of ordered pairs. Notice it doesn't say ordered numbers. Okay, it just says ordered pairs. I could very well have a set of ordered pairs that are words. Oops, back up. For example, I could have an example C here. I could have Ella has a dog. Bob has a cat. So I spells parakeet. How about Sam has a bird? And Joe has a turtle. Okay, this is a relation. It's a set of ordered data. Okay, Bob goes with the cat. I mean, they go together. Okay, they're ordered data. Okay, so this is actually a relation as well. This is a relation because it's a set of 3 coordinate points. And this is a relation because, again, it is a set. It's a set of ordered data. The 1 goes with the 3. This is just another way of writing a set of ordered pairs, right? It's more of a T-chart, or what we call an input-output table. So 1, 3, that's a point. 2, 4, 1, 5, 3, 1, 3, 8, and so forth. Okay? These are all relations. A function. A function is a relation, meaning a set of ordered data, that assigns exactly one value in a range or an output to each value of a domain or input. I know that makes no sense to you whatsoever, so let's break it down a little better. Let's look at what a function box is. Okay, so this is an amazing function box. Okay, it's a big function machine. Okay, we're going to input a number. It's going to do its function magic, and it's going to output an answer. So let's put 5 in, and we'll run the machine. It thinks, it talks, and output comes a -2. So we have 5, -2. Let's put another number in. What number you want to put in? 17. We'll put 17 in, and we run 17. We push run. It goes in. Out comes a 10. What's another number we can put in? 100. And we run it. It goes in. Out spits a 93. Let's do something wild here. No. We got 2 more values to put in. I'm going to do something. I want to put in 5 again. I'm going to put 5 in again. I already put 5 in once, right? I'm going to put 5 in again. What do I get? -2 again. Well, how about if I put 5 in again? What do you think I'm going to get? -2 again? So every time I put a 5 in the box, I get a -2 out? Does anybody know what's happening? What are we doing with these x's to get these y's? Anybody see a pattern there? Yes? Subtracting 7. So our function is y equals x minus 7. So when I put a number in, I subtract 7 from that number, and that gets me my output. 5 minus 7 is negative 2. 17 minus 7 is 10. 100 minus 7 is 93, right? However, every time I put a 5 in, I got a negative 2, yes? That means this y equals x minus 7 is indeed a function, okay? If I put a 5 in the box, and let's say I got a negative 2, and I put a 5 in the box again, and I got a 6 out of it, it's not a function, okay? So for every input, I'm going to get the same output out of the box. Does that make sense? If I put 5 in, I'm going to get negative 2. I put 5 in, I'm going to get the same output. I put 5 in, I'm going to get the same output. Okay? Does that make sense to everybody? That is the definition of a function now. A relation that assigns exactly one value of output to each value of the domain. Meaning, all the x's I put in, if I put in an x, I'm going to get the same y value every time I put in that x. Okay? That's what a function is as a definition. Now we need to decide what kind of functions. Put that way. We need to decide by looking at different relations if they are a function or not. Okay, we'll do that here in a minute. Domain. Domain is the collection of all input values, or what goes in the box, what goes in the function box. So the x values are the domain. So in this case, the domain is the input values, or what I put into the box, which is 0, 1, 2, 3, and 4. Okay? The range is all the output functions, what comes out of the box. They're the y values. So in this case, the range would be negative 20, negative 19, negative 18, negative 17, and negative 16. Okay, they're what comes out of the box. All right, now, vertical line test. Vertical line test is the method you use to determine if a relation is a function or not when giving a graph. Okay, so if a vertical line passes through the graph more than once, the graph is not the graph of a function. Okay, this oval or ellipse or whatever you want to call it is not a function. Okay, now look up, everybody, look up here because it goes fast. I don't want anybody to miss it. I spent a lot of time on this. You ready? Okay, here comes my vertical line. You can use your pencil. And as it crosses through your line, I just stopped it here. Right now, I'm touching the graph 2 spots along this vertical line. I'm touching it here and I'm touching it here, yes? This means it is not a function. Okay, now think of it as a function box. My x value or my input was a 3, right? So I put a 3 into the box. And sometimes I get a 3 out of the box. I'll get 3 out. But the next time I put a 3 in, maybe I get the negative 6 out. Okay? So in this case, when I put a 3 in, I have 2 outputs that are possible. I might get the 3 or I might get the negative 6. Does that make sense? That's why it is not a function. Okay. So no, not a function. How about these? Number 2. You can use your pencil as your vertical line and go across your graph with your pencil. So on number 2, if I go across, am I ever going to touch that line, that function more than once? No. So yes, number 2 is a function. How about number 3? No, it is not a function. If I were to draw a line like right here, I actually hit this curve in 3 spots, yes? So if I put in a 3, an x is 3, into the box, I should end up with a 0, or I could end up with a 7, or I could end up with a negative 5. I have 3 options when I put in that number in the box. I'm going to get one of those, but I might get all 3 of them. So, not a function. Okay. All right. This is another way to look at a relation to see if it's a function. This is a relation. It's a set of ordered pairs, right? These are my x's or my inputs. This is what I'm putting in the box. This is my y's or my outputs. It's what I get out of the box. Okay? Is this a function? I'm going to say no. Look right here. When I put a 1 in the box, I get a 3. But when I put a 1 back in the box, I get a 5. That's not the same number, right? So that makes it not a function. Okay? I could also look here. The 3 gets a 1 and the 3 gets an 8. Again, not a function. But it only has to happen once for it not to be a function. So no, it is not a function. It is not a function because when we put 1 in, I can get 2 different answers, and that doesn't work for functions. Domain. Domain. When we write the domain, we have to use funky braces, and they're very, very fun to draw, but you have to draw them. So we have brace, and then the domain is right here. You do not have to write the double numbers, but we do want to write them in numerical order. So 1, 2, 3 is the domain, just separated by columns. There's no indication that these are connected in any way. Okay, it doesn't tell you that they are continuous, meaning they're connected. The dots are connected if we were to graph them, so they're just a couple dots on a graph. Okay, range. The range is the outputs. Again, numerical order, so 1, 3, 4, 5, and 8. Good? Next one. Is this a function? I put 1 in, I get a 5. Did I put 1 in again? No, so I'm going to assume every time I put a 1 in, I got a 5 out of it. Okay? 2, I get a 3. Did I put 2 in again? If I did, I got a 3 again. Okay? How about a 3? I've got a 1 out of it. Did I put it in again? Nope. So I assume that every time I put a 3 in, I got a 1. 4, did I put it in again? Nope. That means every time I put a 4, I got a -2. And 5, I didn't put a 5 in again. So that way I assume every time I get a 5, I get a -5 out. Okay? Is it a function? Yes. Okay, just for fun, don't write this down, but just for fun, if I added a point to make it not a function, somebody raise your hand and give me a point that would make it not a function. Corbin? 2 and what?
4.
2, 4 works. If I already put a 2 and I get a 3 out, if I put a 2 in again, this time maybe I get a 4. That now all of a sudden would not be a function, yes? Okay, good. So it is a function as of now, and the domain is 1, 2, 3, 4, and 5. And the range, remember in numerical order, we're going to do -5, -2, 1, 3, and 5. Beautiful. Do number 6 on your own. Go. Write down what you think, and we'll talk about it. Is it a function? Raise your hand if you think yes. Raise your hand if you think no. Raise your hand if you don't know. Okay, it's split. So let's talk about it. If every time I put a 1 in, I get a 5, right? Every time I put a 2 in, I get a 5. Every time I put a 3 in, I get a 5. Every time I put a 4 in, I get a 5. Every time I get 5, I get a 5. Yes? To me, that is a function. Hey, give me 1 point that would make it not a function. How about 1 and 4? So if I put 1 in again, and this time I got a 4 instead of a 5, now it's not a function. Okay? For fun, let's plot those points and see if it passes the vertical line test. Okay? So these are just points. It's not a line. There's no indication that we're connecting them. So 1, 5, 2, 5, 3, 5, 4, 5, 5, 5. Does it pass the vertical line test? It does, doesn't it? It passes the vertical line test. Yes, it is a function. I don't care if the numbers are all the same. It ends up being a line like this. It does pass the vertical line test. It is still a function. Yes?
Don't we have to end up having an equation that works for it, though, for it to be a function?
Not today. No, a function is any ordered pairs can be a function. It does not have to have an equation attached to it. This equation would be y equals 5, but we are not building functions from tables. That's not what we're doing today. Okay? And these could be just a set of ordered pairs, like a scatter plot. There's no indication that they're connected or it's continuous. Okay? If we are given some sort of an equation, like y equals 2x minus 3, then that tells you it's a continuous function, and yes, you would connect your dots. If you're just given a set of dots, then that's all it is, a set of dots. Okay? But we can still look and see if it's a function or not. Domain. Domain is the set of all inputs, or x's. 1, 2, 3, 4, 5. The range is the set of all y values, which is just going to be 5. And yeah, you got to put the little brackets around them. Fun to draw. Okay. Number 7. This is a funky way of saying the exact same thing. Okay? But instead of a T-chart, they're having little arrows telling you what you get. This first little oval deal is your inputs. I'm going to write that up here. This is your input, or your x values. This oval here is your output, or your y values. So we input a 1, and I get a 2. I input a 1 again, and I get a 4. I input a 3, I get a 6. I input a 5, I get an 8. Is this a function? No, it is not a function, because every time I put a 1 in, I could possibly get 2 different answers back, right? I put a 1 in, I get a 4. I put a 1 in, I get a 2. So not a function, no. However, we still can do domain and range on non-functions. So the domain is the x's, 1, 3, and 5. And the range is the y values, 2, 4, 6, and 8. Okay. Number 8. Is number 8 a function? I put a 1 in, I get a 1. I put a 2 in, I get a 0. I put a 3 in, I get a 3. I put a 4 in, I get a 4. I didn't put any of these numbers in again, did I? Or if I did, I always got the same number back. So, every time I put in a number, I get the same number, right? So if I put in 3 100 times, it shows me that every time I got a 3 out of it, right? Because it doesn't necessarily list all the double points, okay? So yeah, it's a function. What's the domain? 1, 2, 3, 4, and the range? 0, 1, 3. All right, do number 9 on your own. Go. So, is number 9 a function?
No.
No, why?
Because 5 and 1 and 1
Because 5 can't be a 1 and 5 can't be a 3. Pick one, can't be both, right? So not a function. Domain is 2, 5, and 8. Range 1, 3, and 5. Good? Beautiful. Moving on. Number 10. Number 10, this is just another way of saying the same thing. This time, instead of a T-chart, instead of a graph, instead of the funky little ovals, we're just given some ordered pairs. In an ordered pair, what comes first, X or Y? The X comes first, yes? So that means the input is first and the output is second, okay? So when we read this, I put in a 2, I get a 4. I put in a 3, I get a 4. I put in a 2 again, I get a 4 again. I put in a 3, I get a 4. Is this a function?
Yes.
Yes. Every time I put a 2 in, it appears I get a 4, and every time I put a 3 in, it appears I get a 4. Okay? I don't care that all the Y's or outputs are 4. That's totally fine. Okay? But every time I put in the inputs, I'm getting the same output out. The domain is just going to be 2 and 3, and the range is going to be 4. How about number 11? Function?
No.
No.
Go on.
So the function, this one we said no, you're right. I put a 1 in, I get a 7, but later I put a 1 in again and I get an 8. I get a different output. Okay, so that makes it not a function, so no. Our domain is 1, 2, 3. You don't have to write the doubles. And our range is 4, 7, and 8. All right? Perfect. 12, do it on your own. Or what are we on?
12. Yeah.
12. Go. I have a slide for 15 or for 12, but is 12 a function?
Yes.
Yes. I put -5 in twice, but both times I put -5 in, I got the same one, right? So that's good. The other things I didn't put in twice, so we're all in good shape. So yes, it is a function. The domain is going to be -5, -4, 3. And the range is going to be -1, 1, and 5. Good? All right. Now we know if they're functions or not. We can evaluate them. And by looking at them, either the T-charts, ordered pairs, or a graph, we can determine if it's a function or not. So now we're going to move into making input and output tables. So this time, we're given the domain. Put the little funky brackets around your domains. Okay, they're not on there, and they should be. So our domain is -1, 1, and 3. And I want to fill out the T-chart here. If the domain is -1, 1, and 3, where do those numbers go? On the X side. Domain is the X's. So -1, 1, and 3. We have an extra box on the bottom of the table, and that's okay. Now, what we're going to do is we're going to plug in -1 into the X to figure out what that Y is. Okay? So now we're going to have to do the function machine in our by hand. Okay, we don't have a function machine to help us. So, Y equals 3 times X, which we're going to say is -1, minus 7. Okay. 3 times -1 is -3. -3 minus 7 is -10. So my output is -10. Plug in 1 every time I see an X. So I have 3 times 1 minus 7. That's 3 minus 7, which is -4. And then we have to plug in 3. 3 times 3 minus 7. I know 3 times 3 is 9. 9 minus 7 is 2. So there's my input-output table. This is a continuous function, okay? Meaning it's a straight line, and it goes It goes to the right forever. It goes to the left forever. So I could actually make my, I could actually oh, hang on a minute. My lost. Okay, so this is continuous when it's given to you in an equation, meaning those dots would be connected to make our graph. Okay, as opposed to just given random points. If you're given an actual function in an equation like that, you will be connecting the dots. Let's look at the next one. Again, we're given the domain. So make your little braces around them. That was a typo. So we're given a domain. Domain we know is the x's, so we're going to fill up that side of my input-output table or my t-chart. And we're going to plug those in. So we have 1/2 times -1 minus 2. 1/2 times -1 is -1/2 minus 2. That's like 2 over 1, yes? 2? In order to subtract fractions, I have to have common denominators. What's going to be my common denominator? 2. So I have -1/2, and I got to make that a 2 on the bottom, which means I have to multiply both numerator and denominator by 2. So -1 minus 4 is -5 over 2. So my output is -5 over 2. If you plug in 0, 1/2 times 0 minus 2. What's half of 0? 0 minus 2 is -2. Plug in 2. What's half of 2? 1. 1 minus 2? -1. So I have -1, -5 halves, 0, -2, and 2, -1. Do 15 on your own. Go. So when we plug in -2, 2 times -2 is -4, plus 1 is -3. Plug in 0, 2 times 0 is 0, 0 plus 1 is 1. Then 3, 2 times 3 is 6, 6 plus 1 is 7. Good? All right, moving on to evaluating functions. All right. F of x, g of x, h of x are all fancy ways of saying y equals. Okay? Now, why do we not call them all y equals? Here's a scenario. Let's say you are working on this massive problem for this international company. Okay? And you've got a list of 20 different functions. And they're all y equals this, and y equals that, and y equals this, and y equals that. Okay? However, you are working on this problem with somebody in Ireland. Okay? And so you call the dude in Ireland and say, I think I figured it out. I think if we plug 4 into the y equals equation, we'll get the right answer. And the dude from Ireland goes, I got 20 equations. They all start y equals. Which one are you talking about? And the guy's like, you know, the 5th one up from the list. And the guy says, well, mine are all mixed up. I don't know which one is the 5th one up from the list. Okay, so there's lots of confusion, right? If they're all y equals. So, Will, pay attention. So what the mathematicians decided to do a long time ago is say, hey, let's name functions so that when I call the dude from Ireland, say, hey, I think all we got to do is plug in 4 in the g of x function, and I think we're good. And the guy can look at his, even though they're all mixed up, find the g function, and know which function the guy's talking about. Okay, so it's a way of naming them, okay, to keep organized. And if anything, mathematicians are organized. So, we can consider this function Fred, and this maybe is function Gerald, and maybe this is function Harriet. Okay, whatever. Okay, now, Blake. Now, this parentheses with the x in it, okay, what does that mean? So we know this is function Fred, but the parentheses with the x means the variable used is an x. That's all. Function Fred with the variable x is equal to this. I could make some other functions. I could say function p of m, that just means m is going to be my variable. That's it. I could say k of p, and that just means that the variable used is p. Okay? So that is what function f means. Function f with the variable of x is this. Function p with the variable m is this. Okay? That's all that means. It is a fancy way of saying y, though. This could be just y, and that could be y, and this could be y, and they'd be the same thing. Okay? The y is the output functions, right? So the f of x has a value just like the y would, and it is our output function. So, when evaluating functions, we want, this means, in function f, that's the function we're playing with, so we're playing with Fred, and instead of writing the variable x, I'm going to write the number 3. That's what that's saying. You did a problem just like this on your warm-up today, but your problem was written more like this. Y equals negative 3x plus 8, and I said evaluate when x equals 3. Right? You did this problem on your warm-up. Something very similar to this. And so what did you do? We just plugged 3 in every time I saw an x. Okay? Except this time, when we're dealing with functions, instead of writing y, we are going to write f evaluated when x equals 3 is equal to negative 3x plus 8. Negative 3 times 3 is negative 9, plus 8 is negative 1. So function f evaluated when x equals 3 is negative 1. That's all there is to it. Okay? It's telling you what function to plug that number in to get your output. So my 3 is my input, and when I plug it in, I get an output of negative 1. Look at number 17. This time, I'm using Harriet as my function. So every time I see an x, I'm going to put a 4. So h of 4 equals x, which I know is 4, squared plus 1. 4 squared is 16 plus 1, which is 17. So function h evaluated when x equals 4 is equal to 17. Do number 18 right now on your own. Go. Okay, we should get 15. Now, there might have been a mistake here, so everybody take a look up here. So we plug negative 2 in the g function. So it's going to be negative 2 times negative 2 plus 9 minus negative 2. So negative 2 times negative 2 is positive 4. Then we have the plus 9. What's minus negative 2? Minus a negative means a plus, yes? When you have two negatives back to back, minus a negative. So minus a negative made a plus 2. So we have 13 plus 2, which is 15. Okay? You can't just ignore any of the minus signs or negative signs. All right. Last set. This time we're just going to do some different things with these functions. So when I plug in 1 in the f function, I'm going to get a number out, right? I'm going to get an output. When I plug 4 in the g function, I'm going to get a number. I'm going to get an output, right? So what this is saying is we're going to take the output of this and we're going to add it to the output of this to get my final answer. So what I need to do is find out what f of 1 is, first of all. So in the f function, I'm going to put 1 in for x. So that's going to be negative 3 plus 8, which is going to be 5. In the g function, I'm going to put, so in the g function, I'm going to replace x with 4. So negative 2 times 4 plus 9 minus 4. That's going to be negative 8 plus 9 minus 4. 1 minus 4, that's negative 3. Yes? So g of 4 equals negative 3. So back up here. F of 1 we know is 5. G of 4 we know is negative 3. What is 5 plus negative 3? Or 5 minus 3, which is 2, is my final answer.
You don't have to put the f of 1 or g of 4 in the answers. You just write the number.
F of 1 is equal to 5. So instead of writing f of 1, I'm going to write what it equals, which is 5. G of negative 4 equals negative 3. So instead of writing g of 4, I'm going to write negative 3. 5 minus 3 is 2. 2 is my answer. So if we look at the next one, this time we are just going to find out what f of negative 1 is. And when we get that answer, we're going to multiply that by 3. That's all that's telling us to do. So first f of negative 1. In the f function, I'm going to put a negative 1. Find out what that output is. So that's going to be 3 plus 8, which is 11. So f evaluated when x equals negative 1, or the output, is 11. So I can then do 3 times this output, which we said was 11, and I get 33. And there's my answer. Do 21 all by yourself and we'll call it a day. All right, so we plug 2 in the h function. 2 squared plus 1, that's 4 plus 1, that's 5. So h evaluated when x is 2 is 5. Quiet. We put 5 in the g function and I work it out, I get negative 6. So 5 minus negative 6. What's a minus and negative? When they're back to back, what do I do with those? make it a plus. So 5 plus 6 is 11. Okay, can't forget any negative signs. If this is a minus, it stays there no matter what. If we have a negative, it's a negative working there. Okay? And we are done for the day. Our homework is a worksheet that I'll pass out to you in just a minute.